Good morning and welcome to the 2018 AP Chemistry FRQ Question 6 walkthrough. Today we're talking about this problem which deals with galvanic cells. As for reference, this will not be on the 2020 AP Chemistry exam, or should not, but we're covering it for sake of completion and future practice. Question 6 says a student sets up a galvanic cell at 298 K, room temperature, that has an electrode of Ag solid immersed in a 1 molar solution of Ag plus aqueous and an electrode of Cr plus immersed in a 1 molar solution of Cr3 plus aqueous, as shown in the diagram above. So these are standard solutions, standard setups. A says the student measures the voltage of the cell shown above and discovers that it is 0. Identify the missing component of the cell and explain its importance to a non-zero voltage. So if you look at this, imagine we're an electron. We're an electron right here. It's going to go down, up, through here, through here, through here, through here, down, and where do we go? What are we missing? Well, we're missing this salt bridge. The salt bridge allows the electrons to flow between the two cells and allows the balance of the electrons to keep going. A more accurate or complete way to say this is that the salt bridge allows the migration of ions or negative ions to keep the charge balance in both cells so you don't have a constant accumulation. It allows the flow of electrons to complete. And that is what's missing. Once you add it, you can do B, which we'll talk about now. Part B talks about the half reactions after you fixed it. So it says the student adds the missing component to the cell and measures E cell to be positive 1.54 volts. As the cell operates, Ag ions are reduced. Remember, reduction is gain of electrons. So this is your reduction reaction right here. Use the information in the table below to do the following. Calculate E for the anode. Okay. Two acronyms we need to keep in mind. First is oil rig. Oxidation is loss of electrons. Reduction is gain. Okay. As you oxidize, you lose electrons. As you reduce, you gain electrons. The second is anox red cat, which tells us that at the anode, oxidation occurs, at cathode, reduction occurs. The two of these combined help us figure out what we need to do. This tells us that because Ag is being reduced, it's the cathode, so we're looking for the anode, or what's getting oxidized. We go look at our handy dandy equation chart, and the equation that we should find is E cell equals E reduction at the cathode minus E reduction at the anode. This is because there are no standard oxidation potentials. There's the standard reduction potentials, which we just subtract to give us the oxidation values. At that point, we just need to plug in our values. The overall value for the cell is 1.54, as notated here. The cathode, where the reduction is going on, is the 0.80 minus the anode reduction. Solve for your unknown. Your E standard at the anode reduction would then be equal. Solve this out. Subtract the 0.8 to the other side. Don't forget your negative sign. Gives you negative 0.74 volts. And there you go. Just some factual information that you just need to be able to piece together. On the other hand, it says write the balanced net ion equation for the reaction that occurs as the cell operates. We have already been told that the silver is being reduced, which means it's gaining electrons, which means that it's going to be Ag plus plus E minus goes to Ags, aqueous here. So whatever's getting oxidized, or in this case, the chromium, which is getting oxidized, needs to flip and go the other way to be a oxidation or losing of electrons. Cr solid plus, or Cr solid goes to Cr3 plus Aq plus 3E minus. Now, we can't add these directly because there's an uneven amount of electrons. 1 electron here, 3 electrons here, ain't gonna work out. So what we need to do is triple the top to get the appropriate amount of electrons. And now I can take the two of these and add them together. The electrons will be canceled out, but let's just go through that entire process. Okay, notice how we have the electrons on both sides, so they'll just cancel out, which means my overall, or my end, net ionic equation is going to be 3 aqueous silver plus ions plus chromium solid goes to 3 solid silvers plus chromium 3 plus aqueous. And just to double check our work, we have 3 times plus 1 is plus 3, plus 3. Our charge is balanced. This is done. B, part 3, asks us to calculate the value of delta G standard overall for the reaction in joules per mole reaction. The equation for delta G for a galvanic cell is delta G equals negative NF E, where E is the cell value, F is Faraday's constant, N is the moles of electrons, which means we need to look at our chemical reaction again. This is the balanced reaction we found in the previous step, but there was this 3 electrons on both sides that we canceled out. And we need that for this step. Now, if you crossed it out or forgot how to get there, we can always go, okay, what's the charge change? This goes from 0 to positive 3, so there needs to be 3 electrons moved. That's the other way you can get there. But once you have that, this is just a plug and chug equation. We have negative because the reaction says so, 3 moles of electrons per 1 mole reaction. Faraday's constant is 96,485 coulombs per mole electron. Moles of electron are going to cancel out. And it is 1.54 volts, which is the same as joules per coulomb. Coulombs cancel, moles cancel, leaving us with joules per mole reaction. And like I said, it's just a plug and chug equation. Multiply it all out. 3 times 96,485 times 1.54 gives you negative 4.46 times 10 to the 5th. Don't forget your units, joules per mole reaction. There we go. And that is 2018 AP Chemistry's FRQ number 6. Thanks for watching. Have a good day.